I'm one of the hosts, Oliver, and
I'm Rachel. Welcome to the
the
TheForkJoin,
Fork
everyone.
Join.
Today we
Yay!
have an awesome guest. Oliver, I think you're going to introduce them.
Yeah, so Sam is my good friend. He is a researcher extraordinaire at Intel, and he knows a bunch of cool stuff about floating point, hardware, and also recently is become an expert in programming languages. So I'm very excited. Yes, a top tier expert in programming languages. He goes to all the conferences. And also, I'm very excited to be hearing about hardware because, a lot of PL people are so removed, so abstract from the hardware that they work on, uh, that, maybe they should start to pay a little more attention about the bits and bobbles. So I don't know if you want to do more of an intro of yourself, Sam, if I missed anything.
I think I'll probably just water down your introduction and say that I'm far from a PL expert. Oliver just believes that I'm a PL expert because I know anything about abstract interpretation. And I
Does
also have my little imperial hat as well, PhD imperial at the
Oh
same time.
yes, I missed that. Yes, he's not only at Intel, he's a PhD at Imperial. But does he not
Other than
sound
that,
like a does he not sound like an expert in PL if he knows abstract interpretation? Anyways, the first topic we have today is intros and what is hardware. So the question I would love to ask Sam is, what makes you excited about hardware, and what is this hardware thing in the first place?
okay. So hardware, I guess, is, people might not think about how we write. It's not that different from like writing a software program, other than you kind of fundamentally change how you're thinking about computation. So you need to think about your bits and exactly what do those bits mean. Whereas in any, fancy, any programming language like C or whatever, that's your type system basically resolves that for you. And we kind of put a lot more of the type system onto the user themselves. So really, a computer chip starts life looking like just lines of code. Like it's nothing different from a software program, and it like connects some bits together, and you send around some data, and eventually you compute something. But there's a whole massive process from writing it in a programming language. You do some really complicated tooling. Basically, everything is NP hard problems, where that means that just they're really hard to solve. So everyone in the kind of tool space in hardware design basically throws their hands up in the air and says, it's a really hard problem. So we just use some heuristics and some metrics and things like that to kind of make it simpler and more efficient, and actually have a good go at solving the problem. And then in my land, I produce, fixed hardware. So we will go and generate actual silicon that goes off and gets fabricated. Fabricated is just a fancy word for saying manufactured, um, into actual physical silicon, which is, building block of most hardware these days. There's lots of fancy other ways you can do it, but basically silicon dominates. And this is what, the chip shortage is in the world. It's all been about. It's been about shortage of manufacturing resources, shortage of silicon, all these problems that kind of world has been talking about. But from a hardware perspective, there's been a massive explosion in the number of people interested in building hardware. So like Intel, AMD, other kind of classical NVIDIA, whoever you want. There's not that many companies 20, 30 years back that were actually producing computer chips. And
Yes, you
now,
already said a bunch of interesting things there. Let me repeat some of them back. One of them was, okay, hardware is just like normal programming, you said, except that there's a bunch of like super hard problems that have to happen to go from your high level code to actual silicon. And then you said that like we have these big companies all producing their own chips now, so the hardware space has changed a lot recently. And you also said something about, like the hardware being subtly different from normal programming despite being written down in another programming language. And so I guess we'll definitely be diving more into that in the rest of the show. But you still haven't answered my one question, which is what makes you excited about hardware? We have some sense of why it's hard and why it's different from software now. But what's exciting about hardware to you, and like why do you work on it in the first place?
good question. Okay. So I'm a mathematician first. My undergrad was in maths. And the way you generate hardware is an entirely different way to think about maths. Everything is like you've got some finite precision. You can't compute. The real numbers mean nothing to a computer. There is no concept such as the real numbers, whereas mathematicians love the real numbers. But then you have to turn into this different world, and you can do, the great thing about hardware from our perspective is you do insane maths that, doesn't really make sense in any other setting, and you get away with it. So that's what I get excited about. Like, I build multipliers. I build circuits that literally do A times B. And it's super exciting and it's super fun. And I know
A
that's
times B is
ridiculous.
very exciting.
And like everyone else in the world writes a multiply symbol. But the reality is there are like thousands, millions, billions of ways that I can go and generate a circuit that does that multiplication. And like for every different application, for every different, particularly different inputs. So like we've got all these new machine learning tricks that people are bringing in. It's a whole new hardware question. So everything is different, everything is custom, everything is bespoke. So it's a really exciting space. That for me, that's what gets me going. That's what makes me excited. But
So you love
I'm
hardware
super
because we have some funny and interesting math challenges in the hardware space, and they're like practical
Like,
to work on.
yeah, I guess your answer is really interesting because it comes from this angle of like, my background is math, but like it almost feels like it's where the rubber hits the road. You have all of these abstractions that you like to write down, or we like to write down as software programmers, including the multiply symbol, which, fun fact, didn't always exist in real hardware. And it's someone's job to turn that into fast and correct circuitry that can give you those abstractions. They can actually realize those abstractions for you. Um, yeah, so I guess this answer jives with me too, even though I don't identify as a mathematician. I just like seeing what the real thing is under the hood. It's a very engineering focused answer for me, which is like you take these abstractions and where are they rooted? Well, they're rooted in physics and all of these complicated circuits we're building. Um, and yeah, there's a lot of choices, right? The choice of the fact that people still are building new kinds of multiplier circuits is crazy to me. It's one of those problems that I'm like, it must be solved. We must know how to build good multipliers. Nope, we don't.
No, we
We know
don't.
how to build some kinds of good multipliers for some things, but not really everything.
So
but I
would
think
it
for you,
be?
Ratchet,
Oh,
a
sorry.
parallel is you get excited about compilers, right? Maybe I'm wrong to brand you as a bit of a compilers person, but you're kind of like an abstraction layer up from me, right? Someone types in some high level constructs to you and you turn them into instructions or whatever that may be, or, compose them down to something lower level. So you're just going, one tier higher than maybe I think about on the day to day.
Well, yeah, it's not wrong to label me as a compilers person, but my compilers end up generating circuits. So I feel your pain and your love at the same time of this area.
Would it be safe to say from what we've said so far that hardware is a purely academic area of study with no practical application?
Are you trying to troll other?
But yeah,
Um,
like what I think we should still talk a little bit to the audience about why hardware may matter. Like I have a processor. It's done. We already got a processor, you know? Like but Sam mentioned something about like we still don't know how to multiply numbers correctly or like the fastest way in circuits. Or that maybe there's many trade-offs perhaps.
I mean, it's all an exploration space. There's trade offs between, so what people probably don't think about is that your computer chip is what, like that big, something like of that scale. And every millimeter square on that chip costs us, as a company that actually produces chips, a really non-trivial amount, dollar amount per little chunk like that, right? And so what we're trading off here is you got to go fast enough to keep up with the competition. You don't want to draw too much power because power, so this is what all the machine learning people are super worried about, all the data center people are super worried about, is my data center consumes megawatts of power every day, right? That translates into running costs, et cetera, et cetera. But also, you got to do the tricks that keep you fast enough and minimize your cost base to actually produce that thing. So I don't know. It's like producing a really efficient car engine or something like that, right? You want to be able to fit it in a small car, keep it lightweight. There's all these trade-offs to explore between, the classic American approach of shove a massive V8 or something in versus a more European or Japanese approach of shove a more efficient but smaller engine in your car.
Yeah, I like
Things
the
like that.
analogy.
So all of that is really up for grabs. And particularly the last 10 years are an entirely different game with now everyone producing their own chips. It's a much changed world.
Yeah, I think like I've previously maybe said this before, but like when I think of circuit design and architecture, it feels very different from software design or like general software design because you live and die by two numbers. You have your area number, which is the amount of space you have, and that's all you get. You don't get to like wiggle around it. You have like this square millimeter area, and you need to sort of keep your design inside it. So you get your area number and you get your frequency number, and you live and die by those numbers, right? Like if you don't hit your frequency target or you don't hit your area target, you have to rewrite your code. You have to rewrite your circuit. You have to make it have a different kind of trade-off than you started with. And so like it feels like a very complex multi-objective like optimization space in a way that like, average software programming, you might care about, speed or performance, but the way we quantify performance of software programs is just like hilariously bad compared to the kind of concrete numbers that architects are working with all the time, right? Like you run the tool and it tells you you did a bad job, try again, right? In a very concrete way, in a way that software programs don't. You look at your flame graphs and like, this bar is like slightly big, whatever, who cares? But I think with hardware, there's a big trade-off space, it feels, and then there's also like very concrete numbers that characterize that space for you, but they're not very instructive, is my feeling, right? Like, so this is something I've been curious about, which is when you're doing this process, like, tell us like what the daily life of a computer architect is, someone who's building these circuits. Like, what is your daily process? What is your like code compile edit cycles look like, and what do you think about when you're doing that?
And definitely reveal as many corporate secrets as you can in the process. But I'm just joking, just to be clear.
Of
For
course.
contractual reasons, I am joking, obviously. Yeah, I don't know. It's. I don't say I can't really claim that I have massive industrial experience. Like I'm not at the sticky end of production cycles that often, but in general, you have some spec. Everything starts from a spec, and in general, in big companies like Intel, the person who writes the spec is separate from the person who actually goes and writes the circuit design in a programming language. In other companies, I think other companies have different models where the architects will actually go and actually implement the circuit themselves. But that spec can be something like just written down in words, can be something like a C model that actually we can go and test what it's doing, or it can be the spec can be your previous generation hardware. And so you take that as your starting point, and then you go off and you understand the maths behind it. So this is where often your spec is actually like words that can be really helpful. So this is a big problem, and there's a big emphasis on sort of machine readable specs and things like that, and expressing what is your circuit trying to do in just maths. Because as soon as you have any sort of C model or something like that, you've kind of expressed an algorithm or an implementation of it. So you've driven a designer in a particular way. And so they're more inclined to go for like one particular implementation rather than thinking about maybe the best way. So you kind of want to give a designer a fairly blank slate in a way so that they can go and actually do the optimization, the design space exploration themselves. And then I traditionally will just write some RTL and I try and hit something functional. So for me, I have verification tools in my flow. So I will write a circuit and I will have like a very basic implementation, and I will compare these two things and make sure, hey, have I got them equal? And this is just what we call equivalence checkers, which are just tools that you throw two designs in and it basically says yes or no. It's like a SMT query or SAT query. It's that kind of simple, but they're kind of bigger and more expensive and all this sort of stuff. But they basically say, yeah, it's functionally correct. And once you start from a basis of functional correctness, then you do the churn on the optimization, what will be things like toggling, like, moving signals around, moving registers around, the much lower level design optimization choices. So what Theo, who is my boss, always talks about is that kind of there's this pyramid of change. So you have kind of your algorithm, which gets fixed fairly early on and doesn't really change that much. You then have kind of lower level choices like what precision are you going to use throughout your circuit and what number formats are you going to use. They change a bit more, but a bit less than the next step down, which is kind of doing like word level optimization. So doing arithmetic optimization. So that's things like, manipulating pluses and minuses and all that jazz. And then kind of at the lowest level, you do a lot of bit level manipulations from the actual tool perspective. So when I've written my circuit at like A plus B plus C, whatever it may be, I then throw it into a tool called logic synthesis, and that will go and generate what's called a netlist, where that netlist is basically just
Okay,
gates.
Sam. All right.
Yeah,
This is
far.
very
We're
good. We're too far, but there was like you wrote down your circuit in something, and then you called something else RTL, which we weren't sure if it was the thing you wrote down. And then there was a verification tool, and then there was a pyramid of optimizations. And then there was logic synthesis thingy. So let's go step by step through those real quick.
Break it down.
Yeah.
Okay, step one, you have your spec.
Good.
That can be written in words, it can be written in C. Step two, you have a piece of RTL. So RTL stands for register transfer level. That is, something written in Verilog, system Verilog, some sort of hardware description language is what we call them. Step three, you chuck that into an equivalence checking tool that says, are you functionally correct? So this is what people talk about verification. Step four, chuck that into kind of logic synthesis, which actually goes and takes that sort of word level description. So you're talking about A, B, C, kind of add the two things up, and then you're dropping it actually down to like how your software compiler drops into an instruction set now, or like assembly code. This is where we drop down into what we can actually build out of silicon.
So and what is
what
that called that you can actually build? Yeah.
So we call this a netlist, where a netlist is made up of gates. Oh. So your gates literally are looking at two binary digits, binary bits, if you want, and actually doing something to those things. So it's literally ones and zeros, and they get turned into zeros and ones or whatever, depending on the particular gate. And so it's very similar to how, a software compiler does its high-level thing into a very low-level thing that your CPU understands. We take a high-level thing and drop it into a low-level thing, which our manufacturing teams actually understand. And there's a whole design flow that happens after that about putting wires in, doing like, power optimization and all that sort of jazz, which I have no idea about, I'm afraid. So there's a big phase that goes on afterwards before you basically send a blueprint over to your manufacturing team, and they can go and actually do a really complicated process to produce what eventually ends up in your computer.
All right, we have some great questions from chat. I like that explanation, the step-by-step. But one of the questions we had, which is very relevant to the connections to programming languages, and Rutchin and I are in programming languages, and so is some of our audience. The question is, do you also write the model for the verification tool to compare against? Or do you also even write the verification tool itself? Or is that someone else's job?
So in an ideal world, these are all separate people. So in a big company like Intel, we have the manpower that you can have your wall of silence, and there shouldn't be any interaction between the person writing the verification model and writing the actual hardware implementation. Because then you basically get a nice separation of duty. Both people don't make the same mistake. So I think, and then the verification tool is typically produced by a vendor. So a big company, these are called EDA companies, but this stands for electronic design automation companies, that basically produce tools for companies like Intel, AMD, NVIDIA. We all pretty much use two companies, maybe three companies.
That's really
And
interesting. I didn't know that. So these problems are sort of so hard that even giant companies are like looking to other companies to build the verification parts. Is that sort of a characterization of why they look to other companies?
uh, yes, and also it provides accountability. So
Ah, okay.
you kind of want everyone in the industry to use well-tested tools, right? And if you're only hitting it with your designs, that maybe you've got a very specific way of doing things, and then you maybe change, right, later on. Maybe you don't see this problem. So I think one issue they once upon a time had was something to do with front ends. So two tools shared the same front end, and that front end had a bug in it, basically.
Uh-oh.
And so both the tools agreed and it was all happy, but there was actually a problem. And so, things like sharing a front end, all that sort of stuff can have some hideous, nasty bugs in there. And if you're selling formal verification tools, you've got to be bulletproof, like absolutely bulletproof, because people are spending billions on the results of these things.
But Sam, we don't verify software, and we have bugs all the time and it's fine. So what's the point? Another
Uh,
loaded question, perhaps.
of course. And the point being that you can fix software with a fix. You can push it over the network and you can update and you're hunky dory. You haven't done anything dramatically wrong, but it's exactly the same way that Toyota has a problem with its handbrake or something like that.
All
It
right.
has to do a recall on the entire stock of those cars
The car
and bring them back
analogy,
in
yes.
to actually, sorry, I made not car analogies. I'm
They're
not
good.
actually
They're
that into
good. They,
cars.
they make sense. Yeah.
Um, and so, hardware is exactly the same. We can't fix it on the fly. Sometimes you can do firmware to actually work around things. And that's how a lot of hardware bugs get resolved. But the most famous one, which everyone gets bored of hearing about, is that an Intel processor couldn't do division back in the 90s. And they had to recall all of the computer chips and then cost them a huge amount of money. Can't remember what the figure was, but exactly why any company that produces something physical and real, you can't just change it.
Kind of a disaster, yeah, if something goes wrong. But it's also very hard to do formal verification. So it's interesting.
Yeah.
There's a growing
There's sort of
community of
a
software. God,
please finish.
there's just a growing emphasis on software verification now, though, I would say.
Yeah. One thing I was pointing out is there's an interesting thread of questions in our chat, um, where one of the things you mentioned is that you design your circuits in what looks like a programming environment. You write programs or things that look like programs, and then you run a compiler, right? But of course, that's a lie, Sam. I've caught you in a lie here. Just kidding. But really, it's a very different experience to work with hardware for some particular reasons, for the reasons of optimizations and sort of the way these compilers work. They're often solving, as you said, NP-hard problems. Um, so one line of question here was that you talked about netlists, but you mentioned that they don't necessarily always have the wires. And so the question here was like, even the netlist doesn't have any physical wire routing. And if we're sort of slowly refining our designs, we're adding more physical constraints like, oh, these are the gates we're going to use. This is how we're going to connect them. This is how they're sort of laid out in space. How does someone know that the final design is actually going to meet their power performance and sort of area requirements that you've talked about previously?
So I think this is really where you have a separation of duty just to make it even achievable to produce this mega, a computer chip is super complicated to produce. And so you have different people who will make different assumptions. So us as front end design people who actually design, write the circuit and define the functionality of it, don't tend to put that much thought into how are the wires going to get connected up. But inside the tools that we use, we hope there is some, awareness of what's going to happen later on. So when you're producing a netlist, right, you would hope that the tool has some awareness of what is going to come on later down the line about, actually these things have to be connected by wires. So maybe let's not have one particular area in my circuit that has a million wires going into it, right? That's a fairly easy thing to detect when you're doing a compilation or whatever it may be, that this is going to be a problem and we should try and avoid that. So from my perspective, I just hope that the tools deal with that. But of course, what can happen is that we get feedback from later down in the design cycle that says, hey, what gets called wire congestion, where you have, way too many wires than can fit in a particular area in your chip. And so then they will kind of try to punt that back up to us and say, can you redesign your circuit to try and think about different connections? I personally haven't really experienced that. Often it will be the teams that run those tools that will then kind of drive those tools to figure it out for us. Because it's super hard to understand how the kind of high level description you have is going to translate into wires. And particularly, I will give Theo's analogy here. That is, if you're packing a lorry and you've like got lots of different boxes, if you just change one size of the box, you shrink one of the boxes by half, then the optimal packing of your lorry like changes completely. There's not necessarily any correlation between those two things. And this is what we suffer from a lot.
Yeah, so there's almost like a lack of incrementality in the way these tools work, where a very, very small change here and there might dramatically change your outcome of the shape of your design and whether or not it fits. It is true that if you like ever try to play with even FPGA tools, which are again another kind of circuit simulator technology that more hobbyists tend to use because they're easier to get into. One of the biggest problems you run into very quickly is that the thing that stops you from getting your design working is often wire delays. It's not the physical design that you build; it's implicit wires that you wrote. And so it's like your LLVM compiler saying you have too many branches, or your branches jump
Try
at too many
again.
locations. It'd be
Yeah.
fine if they only jump to this particular location 5 times, but they're jumping there 6 times, and that's not acceptable. Um, and so it's very hard to take that kind of feedback. Like these tools, it seems, will give you feedback saying this wire will not fit. But it's very hard to, what you're saying is very hard to take this information and turn this into like high level feedback that you look at your design and you're like, oh, this A plus B plus C is actually the problem. And I can sort of change it in this way. It's not very, again, the problem seems to be that it's not very, it is informative, but not very instructive in some ways.
Yeah, I guess we're getting at the two problems in hardware. One is the non-local changes. Like if you change one little thing, the packing problem completely changes. But the other problem is like you'll often have to break through the abstractions or like think about the lower level details while you write the higher level specification of the circuit just to like deal with these physical realities, which is pretty interesting and not something programmers usually have to deal with.
Certainly, I think, how often do software people think about the instruction set that their particular compiler has or their particular CPU has, right? Only at the real hardcore end of software design do people think about this is going to run on this thing, so I'm going to optimize the hell out of it. Like this is what there was a great Google DeepMind thing recently about. We managed to do sorting really efficiently, and it like basically just had, if you're trying to sort three things, then do this exact assembly set. If you're trying to sort four things, do this exact assembly set. And that's like kind of the hardware problem, right? Like we're basically doing the assembly level writing.
Right.
Okay, we had an interesting question in chat about a specific tool called Forte, but the more general thing they're asking about is symbolic trajectory evaluation for verification. Do you know anything about this?
Yeah. So I think Intel formal verification has had an interesting cycle. So there was the whole division bug we had back a long time ago. And there was a man named John Harrison who kind of started a whole theorem proving, was probably one of the founding fathers of theorem proving for hardware. That may not be entirely correct, but he was certainly one of the big names in it. And that all has kind of slowly died off to an extent as the hardware industry has moved more towards vendors producing formal verification tools. So we actually had some of the Amazon automated reasoning people in recently. So one of the guys, Daniel Cronin, came to visit us at Imperial, and he talked about in hardware, it completely makes sense to have, external companies producing your formal verification tools because it's so important and so valued, and they kind of have an idea of how to do it. And this whole equivalence checking that I've talked about, give it two designs and say yes or no, has really taken off and has pretty much dominated the industry. Forte and symbolic trajectory, I think, still exists. It has been around for a while. I don't know entirely its prevalence anymore, but it's still alive, it's still kicking, but it's a
What is this
particular Intel.
symbolic trajectory thing? Is it similar to SMT solving, which we didn't really explain either?
Ratchet, are you better to do symbolic trajectory? I can do it, but
No,
I would do it
actually,
badly.
if I had to guess, there would be some sort of like bat sensitive evaluation, but I've not come across this term before now.
Okay, none of us know
Where
it, but
you
we can
well,
talk a
so I
little
can
bit about like modern SMT techniques, which
so
is
I can
like,
give symbolic trajectory a high level overview.
oh,
So
okay.
it's a big thing at Imperial as well.
Ah.
Um, so there's a tool called CLE, which is one of the
Oh, it's
big
the
Oh,
symbolic
CLE thing.
the CLE thing, yeah.
So is this model
Um,
checking? Is that the same thing? Or is that
it's
different?
related.
Okay.
It's where you basically evaluate symbolically kind of all paths through your program. It's very relevant for your whole title of your thing because every time you hit like a branch in your code, you then need to evaluate both paths within that code. There's a whole reachability analysis, like if I have nested if statements and things like that, can I actually trigger these various different if statements under certain conditions? So the idea is to kind of symbolically model all of your different variables through, but also understand what constraints you're reaching as you're going through, and like know that there is some, certain data can't hit this point, so you won't ever hit this as you won't ever hit this exception. So it's quite a semi-popular thing that has scalability issues, I think, basically. And hasn't really taken off to its full, but it is used in quite a lot of places. Hardware design does use it quite a lot.
Interesting. Well, it might be a good time to, yeah, move on to a new topic, which is verification. Uh, we don't have any specific questions yet, but do you want to talk about maybe your
sure.
personal work in the area, or what do you think, Ratchet?
I think it'd be good to. I think we talked at a very low level about what ST is and how like you're evaluating and modeling things, but let's put some like concrete meanings behind these words. I think literally every single episode of this show that we've had, we've talked about specifications. So
Oh, yeah.
let's talk about some specifications again. And then let's talk about sort of the very high level idea of how symbolic modeling works. Why is it called symbolic, first of all, right? And why do we care so much about it in the hardware context, right? I think like for if you're an average programmer, you don't really think about formal verification or symbolic modeling or any of these words. But I think it would be important and interesting to contextualize sort of how this works in the hardware industry. You've already motivated pretty well why we care about it, which is that anytime you produce something physical, if it's wrong, you really have no other choice apart from sort of recalling it, right? If it's wrong at the sort of the circuit level, not the microcoded level. So let's talk about like what the concrete things are, and maybe we can start with a very simple technology that might be easy to understand for people. Yeah, Sam, questions, thoughts?
Maybe to go to your initial point about what are specs, where do specs come from, and things like that. Particularly in my domain, I do a lot of maths circuits, or a lot of arithmetic circuits. We will have things like IEEE produce their specs that says floating point should do this exact type of computation. So if I produce a floating point adder, namely that adds two numbers in, I presume all your audience are happy with floating point,
Probably.
Yeah.
then, you know, it has to follow this exact behavior. And that's pretty well specified. There are some issues that these things can have ambiguities, but more specifically for my field, I actually work in Intel graphics. So, we're the ones behind the Arc GPUs, and hopefully everyone's positive about those recently, given the performance improvements. My small sales pitch for Arc actually being the hardware being pretty good, and the software is now pretty good as well, which is cool. And it's been an amazing part to be, great thing to be part of that. But for them, DX specs, so DirectX. So you always see if you buy a game or anything like that, it probably says DX12, DX9, DX whatever, right? And probably most people in the audience haven't thought about what DX means, DirectX, but it simply is just a set of specifications, I think, from Microsoft that say this particular part of your graphics pipeline, namely the set of computations you have to do to produce a pixel on the screen, should do this and should produce results to within some error bound on the real number evaluation of it. So traditionally, this is where we get all our specs from, is we have to build circuits that comply with DX, that comply with IEEE. So it's other people often telling us what we should do. And then there's the other branch of when maybe there's not someone telling us what we need to do. And so then we rely on our architects and our kind of senior people in senior sort of experienced positions to actually guide us and tell us, you need to be making these decisions. And you need to be producing hardware that meets this sort of criteria. But there's probably more freedom and less certainty at times than I think people might expect.
Yeah, so you're describing the state of the world as there is, sort of some notion of what is this tool supposed to do when it is designed correctly. So for something like floating point, it's very precise. There's literally an IEEE specification that we've used for decades, and that tells you what floating point is, right? It's not, and it's defined in terms of very low level operations, it would seem, right? So when you build a circuit that does a floating point addition or multiplication, for it to be correct, it must do what the spec says, right? So this is the specification part. I think the second thing that you were getting at is compliance, right? And so that's really where all of these other tools like equivalence checking come in. So can you talk a little more about what does it mean to comply with a spec, right? Like it's like one thing to look at the, like 100-page specification and look at your circuit and be like, it kind of feels right, versus the kind of guarantees you might want if you're shipping a product through Intel or something like that. And so that would be my next question.
This is where separation of duty comes in, and you'll have people that produce like a C model of what the DX specs say we should be doing, and you'll have actual hardware implementation of that. And so you'll go off and make sure that the C model, you can do lots of testing with things like RASTI. RASTI is like some tool that I don't really understand, but it basically mocks up a GPU pipeline. And so that you can then actually run. So this is one thing that one of my colleagues uses a lot, Bill Zorn, who's a big programming languages guy. He's not a hardware person at all, but he's now kind of in our field because he does, let's write C models and let's understand how does this affect what image is going to come up on the screen. So Bill will literally take scenes from BioShock and random games like that and just be like, look, I changed the algorithm and now this picture versus this picture. And so you have people kind of at that higher level doing that stuff.
That's extremely
and then
cool.
You've got,
so
really,
he just
like really
improves the picture that would have come out of BioShock by using like this model.
And it's a lot of like really random things, like if I do this, then look, the lighting looks insane in this picture, for
Uh,
example. So it's the classic thing he will do. Or like sometimes it will just get it completely wrong. Like you'll have a window and the window will just be completely black despite the fact it's daylight outside. So you can clearly see sometimes
see
things
the
are
bugs
massively
that he
wrong.
reveals. I see.
And like often, I mean, 99% of the time, it is like this picture is better than this picture, and you're really having to like squint,
Uh,
particularly over Zoom, to have any clue whether he's actually made a difference or not. But
but enough of those small errors, and like your picture will not look anywhere near like
absolutely,
the original one.
absolutely,
So you gotta be doing this.
absolutely. But so then people like him will be producing these sort of models, and then it's up to us on the hardware side to go and actually reach what those C models produce. And so you have separation of duty. If you have disagreements, then you figure out who's wrong. And maybe it's, probably most of the time it's the hardware people who are wrong, but it can also be the C model people. And then you go back to the oracle that is the spec and make sure you agree that, and it's basically two people or a whole team of people maybe coming to an agreement that, yeah, this is probably what it should be. But graphics is also particularly weird in that compliance often is what does the picture look like on the screen, right? We were just talking about Bill showing me two pictures and maybe this one's better than this one, but someone who's untrained, it can be really hard.
Yeah, I actually really like the example of graphics because it sort of highlights the reality of specification, right? Specification is a very, very hard thing to do precisely because reasonable people differ on what is correct. I think this is true of graphics. This is not true of math, right? Like if you have something like floating point, the specification is very precise and it tells you exactly what is correct. But for graphics, for audio engineering, for I don't know, laying out things or something, what is correctness and how do you define it seems like a really sort of amorphous task, and it's always interesting to hear various different people comment on what specification means to them and what compliance means to them. So that I think that's an interesting example. I wanted to dig down a little deeper into the hardware side of things where you've talked about these tools that allow you to comply with specifications. So let's talk about those tools and why, or how they work, and what kind of magic sorcery are they doing to do this kind of compliance.
One thing I will add to your prior comment about graphics being a little bit less specified. From a hardware designer perspective, we get really excited. This is where the maths comes in. That's fun for me, is that then I exploit the hell out of that. So I will go and, if you give us a tool that does optimization, loads of freedom, basically you say it can produce whatever result you want, then it should just produce like a constant value, right? Imagine you put no constraints on what your design should do and you have an optimizer. It should basically just go and produce zero or something really cheap. And so you can
That's
imagine
right.
ramping that up, and there's a spectrum of if you let me loose a little bit more, I can do more, optimizations, I have more freedom. And so you allow me to
Yeah.
say,
This is like a fundamental tension between specification and optimization, where the more you specify, the more you're sort of tying the hands of everyone who implements it. And so the trick with good specifications is that they tie your hands in very specific ways and leave you free to do many other things. This is true in compilers as well, where you don't want to over specify necessarily. You want to specify correctness while giving people room for optimization, right? One way to specify how a compiler works is say, for this program, it produces this sequence of assembly instructions. And if you ever do that, the only compilers you'll get are very crappy ones, right? And so you're talking about how, like, in hardware design or sort of graphics, when you're building hardware for graphics, you have sort of rough mathematical approximations that you can make use of to get the same output quality on your image. And because the output quality is in some ways more of a specification than the math that went underneath, you can sort of get away with this. A famous example of this is the inverse square root computation in Doom, which does not do inversions or square roots. It's just a shift by a magical constant, and it works, right? The
Yeah,
reason it works is because inverse square root is not the important part. The important part is getting the graphical fidelity that you wanted, which I always think about. So that, yeah, really interesting point.
And just like Sam said, it uses fancy math tricks. It's like, this part of the floating point number already stores like its own logarithm or something like that, and then it uses it. But
Right.
graphics is really cool because the human eye can only see so well, so you can put in these error tolerances, and people like Sam come along and do crazy stuff with it.
Yeah.
Fun space. But the Quake comments on that code are also excellent. I would encourage everyone to look up fast inverse square root, the
Yes.
original code, not the one that's on Wikipedia, because that doesn't have there's some swearing comments, but it's quite entertaining. Sorry, but Ratchet, your original question was, what are the tools I'm basically using to care about correctness, right? I think.
Yeah.
Yep.
Um,
Exactly.
so this is a complicated world of like, there's been theorem proving with its super high barrier to entry, but I would say that's phased out a little bit more. There's still quite a lot of it, but now the industry has trended towards these tools called equivalence checkers, where you have like your C model and you have your circuit implementation in RTL, so your hardware description language like a Verilog or something like that. And these tools can basically take both of those implementations and say, are they equivalent or are they not equivalent? So what they basically do is they build a data structure with both implementations in them, and then apply a bunch of techniques. So under the hood, these things orchestrate SAT, so satisfiability tools, SMT tools, BDD tools, so binary decision diagram tools, and they kind of apply rewriting, they apply some trajectory evaluation just to figure out bit widths and things like that. So there's a whole bunch of tools going on under the hood. Every single tool that I use is completely closed source, so I have no real clue about actually what it's doing, but it produces me an answer at the end of the day.
Okay, but you mentioned this point, this word that you use so lightly, which is saying that these two programs are the same, right? But same is a hard word to define. Now we're really into it, guys. We're talking about what the word same means, right? But one way to say two programs are the same is to look at their outputs, and if they're byte by byte equivalent, they're same, right? But that's not what these tools do. They do something more interesting. So how is the fact that two programs are the same defined? And you mentioned these terms like rewriting or SAT. What are those like fundamental things that these other tools are doing to say that these programs are the same? That now that they don't have access to sort of their like little bit representation that they could look at and be like, these programs are literally the same. Does that question make sense?
As in, I would say same in this context means for all inputs, the outputs match, right? At the same time.
At
That's
the
the
same
only,
time, yeah.
at the same time is the kind of hardware-ish wrinkle of it, but that's not particularly crazy. And the at the same time bit means that, if I continue to feed inputs into this pipeline, so circuits basically will often give you some input, do some computation in one clock cycle. So your CPU, when you see a number like running at 5 gigahertz, 4 gigahertz, that's what's called your clock frequency. That's how fast your computer processing unit, CPU, can actually do an instruction, basically. Or maybe an instruction might take multiple cycles. But you basically have this clock cycle, and this is what we use to basically time our execution through our circuit. And so we're basically producing an output after some number of clock cycles given some inputs. And then you can ask the question, is that always true? If I keep feeding in new inputs, is that always true? Am I always getting the outputs that I need? Maybe I'm setting something internally on one path through that then screws up the next one, for example. And so this is where, if you go back to your, high school maths, you have things like induction proofs. So if I know it's true for all previous up to 10, and I can prove that the 11th one is true, then I can actually kind of do this generalization proof that says this will be true for all time. And so for all possible future. So if you keep running this circuit, subject to it completely melting down or whatever, it will always continue to
Right.
produce the same circuit. So this is one thing that they do really nicely is these induction proofs that say, hey, I actually am correct for all possible inputs and for all time, basically.
Yeah, so you pointed out this very concise definition, which I like, which is that for all inputs, we produce the same output, and then we are equal, right? So there's that definition of the same equality. And then there's the definition that I was talking about, which is literally the text of our programs are the same, right? And so, like in programming languages, we distinguish between syntactic equality, which is the program 1 plus 1 and program 1 plus 1 are equal. So that's syntactically equal because they're the same program. And then there's semantic equality, which is that the program 1 plus 1 and 2 are the same because they sort of interpreted over the numbers represent the same quantities, right? And so the thing you were talking about, the way I'm taking it, is that the tools are doing a mix of both. Sometimes they're trying to rewrite your program to see if they can literally rewrite it to the first program. And if they can, now you have established syntactic equality and you're good to go. You don't even need to do anything apart from that. Or they're trying to do this more complicated thing of semantic equality where they have to interpret your program over, how does this program perform computations over numbers? And then it has to prove that for all input numbers, I produce the same output numbers. And that can be more expensive and sort of maybe easier, maybe harder, depending on the case the kinds of programs you're working with.
What I would describe as functional equivalence is the term we would use. So when it functions, what does it do the same thing?
It seems like a great segue into something Sam works on, which is if you're doing the syntactic equality kind, which is like rewriting or changing bits of your program a bit at a time until you get like that the output is written down the same way, how do you know that each of the little steps was right? And how do you like string them all together into one big proof? I think this is something that Sam's been thinking about a lot recently.
I mean, it's something I think about a lot. Unfortunately, my solution is to use the big overblown tool to go and ensure that even my small steps. So I personally work on a tool that does like a rewriting optimizing, and it basically does a bunch of stuff to a circuit and it breaks it down into a sequence of transformation steps that are very small. And then all I do is I just chuck each of these intermediate steps and says, is this correct? Is this correct? Is this correct? As I slowly transform the program. It's not necessarily very efficient and it uses probably way too much of a complicated tool than it needs to. But the reality is, if you're not proving, in my industry, if you're not proving using these tools, no one's going to take what you're doing. You have to use these big overblown tools, even just for simple transformations. Like the barrier to getting something into an Intel graphics processor is insanely high. Correctly so, but it is insanely high. I think people would be shocked the amount of time and effort that goes into checking, making sure the number of different tests you have to go through. You have to prove equivalence here. You have to satisfy regression tests. You have to satisfy loads of different things, loads of code reviews to actually say, yes, this is it. This is going to be in the chip. So,
but like on the other hand, it's also super cool that you can just throw this giant tool at your particular problem. Like we've already built this huge infrastructure for verification that does things as automatically as possible. And you're saying that even for these little steps, you just ask the big tool and hope that it's fast enough that you can like get a full proof out, and then you string them all together by putting them next to each other, I suppose.
This is what the industry has been driving at for a long time, though. Like theorem proving and that domain was super hard, was done by experts. And really now what they push for is people, mere mortals without, I have no idea about how to do theorem proving, can now just push buttons and things happen. And so you can have way more people using these tools than you could ever have doing really complicated theorem proving stuff, and just get results pretty fast back straight from these tools. And this is, partly because the underlying technology, the SAT, the SMT solvers are also just got really good over the last 20 years. So the underlying technology is good and they wrapped it up really efficiently because they can make absolute fortunes out of it.
Yeah.
Great.
I'll push back a little bit on like the fact that it's easy to use these tools means we should use it for every single step. I know that's not what you said, Sam. I understand that what you actually said is that the social processes around getting something accepted into the physical manufactured chip at Intel are a really high bar. But one thing I guess we should also think about is like we give a lot of crap to machine learning people about how much energy their training and like their inference models use, right? Um, Maybe we're not at the level where like verifying an Intel chip takes the same amount of energy as, I don't know, training ChatGPT, but it certainly is a lot of compute and a lot of maybe unnecessary redundant compute, right? And so finding ways to reduce that burden overall could be a useful goal, could be a novel goal. But again, I understand that the bar to what can be accepted into these chips today is high and not necessarily something we as creators of those tools can go and change and convince people to change.
I think you can imagine, though, I think it's a really great point. And I think certainly we spend a bunch of electricity on synthesizing chips at different clock frequencies, at different voltages, at different, just small changes to configurations. And we spend a fortune on the electricity to do this. And actually, the ML kind of push into EDA, which is the vendors producing these tools for verification and for synthesis and things like that, are actually just running a ton of these, making small tweaks to their various configuration knobs, and then running these tools again and learning based off those results. So they're even, it's way worse. The problem is burning even more energy than just normal computer energy. So you could imagine for sure having like a light version. If you can have this trusted base and then just spin up a light version for when something's easy, or have the tools detect, hey, this is just easy, calm down.
Yeah, I think it's very much an engineering challenge. Like we've abstracted over the automatic tool, but because we treat that as a black box, we're like not willing to touch the solver. We have to like call it a bunch of times instead of putting those simpler things like inside the solver where it can be very fast and efficient. Like your whole string
Right.
of rewrites could be like verified at a lower level in the solver where it like reuses a bunch of information instead of separate calls.
But I think this is also partly that I'm poking from the outside rather than, if I was involved in the development of these tools, then I would understand what's, so fundamentally I don't know what the tool finds easy and what it finds hard.
I
Like
mean,
I can
nobody
guess.
knows what the tool finds easy and what it finds hard. Everyone's always surprised, like which queries are slow, which queries are fast.
Like I feel like at least if you had access to this code, you could have a better stab at it.
That's true. Some people have a better idea. Yeah.
Um, so that's part of the issue, is the poking from the outside when really you want to be integrated inside, right? And that's what they do for. So if you actually do the whole logic synthesis, that, remember, we went back from writing the kind of higher level abstraction down into this gate level thing that I talked about, which is kind of more relevant for your assembly style, if my analogy was correct. You have these tools actually just give information to other verification tools. So in that domain, there's a verification tool where your compiler basically spits out a load of hints to the verification tool and says, hey, look here, you'll probably get it right. So there is just like help. And I think I can think of my tool as just providing help along the way to the verification tool that says, well, I know what I've done. So why wouldn't I tell you this information?
Yeah, it's a good way to phrase it. Like instead of putting all the burden on the one tool, like we may have domain knowledge or specialized things that will help it along. So should
Yeah,
we
there's
move on to another question? Sorry, Richard.
oh no, I was just saying there's sort of work and people who build programming languages to sort of perform verification to actually or automated verification to do this kind of hinting to lower level tools. So one of my favorite examples of this is the F star language from Microsoft, which is a language for automated theorem proving. So it has term proving where you can go down and manually write down some proofs that tell you program A or function A is equal to function B. But it also has the capacity of saying sometimes that function A and function B are equal. And I know this automatically because I'm calling one of the same tools that time you were talking about that do equivalence checking in the hardware design world. A cool thing about SStar's internals is that it emits a lot of these hints for you automatically because it knows the structure of your program and how the proof tool works and what it is good at and what it is bad at. And so oftentimes they emit a lot of hints to get predictable proof performance. This is something we've not really touched yet, but one of the things that obviously comes up when you're using these very complex tools like equivalence checkers, you haven't mentioned this, Sam, but I assume this to be true because all verification tools are slow. The verification tool that you're using is also slow for the definition of slow, that like it's longer than a compile cycle, right? And so if these tools are so slow, you want them to have predictable performance. You don't want them to go from 15 minutes to taking 15 hours. And so people do a lot of work in trying to sort of make it consistent in its proof capabilities. So I guess that's one question that I would have, is that have you run across tools like people thinking about performance engineering, proof engineering, and thinking about the performance of the proofs that they're writing?
I would say no. This is not a big topic in hardware, purely for the reason that as soon as people get a proof or they can nudge it across the line, they're pretty happy, at least in the fields I work in. I'm sure for the people producing these tools, which I don't really interact with that much, then there probably is more of an effort to stability and things like that. But for sure, I think it's probably similar to the box packing analogy. You can turn like, I can take one example where it won't converge in like 24 hours. And if I just change a single like bit width that doesn't change functionality, it suddenly like triggers something to happen in the tool, and then it solves it instantly.
Wow.
I've only got like one or two examples of that, but these big industrial tools are still a bit brittle and they're not completely solid. But I think it's just because it's a hard problem, right? And people are just happy at the moment to get proofs, not necessarily proofs super fast. And it's more about automation and reducing the human intervention, I think, than necessarily getting it super fast. I think people are willing to spend the compute if they get a proof. Don't think it doesn't feel like that's a mega push.
But I think there's like an implicit claim here, which is that the fact people use these tools means that they have some sort of belief that these tools will take some reasonable amount of time, right? If these tools were consistently taking huge amounts of time, people would just not invest in it. So I guess, but maybe what you're saying is that a lot of that work comes from the community of people who design the much lower level tools that aid in the process of proof search and proof solving. And as people who are working on maybe the test suites, the formal verification regression suites, don't really care about this. I think we had like a comment about this where someone was saying that they had a pet peeve about people running massive formal regression test suites regularly when they're proving essentially the same property in RTL over and over.
But I think you have to remember the real like paranoia and like complete terror of any manager in charge of a chip. Like they're completely like terrified of introducing bugs, errors, and if that involves checking the same property 10 times because someone's made a comment change, like it happens. And I think also
Right.
that you have to remember that the verification world is nowhere near as mature as hardware world, right? So we've been doing chips for what Intel's 50, 60 years old or something as a company, but the verification is still relatively young, right? Like only really since 90s or 2000s has it really taken off as a topic as chips became more complicated. So there's not that many people. A lot of the time it's been about just bashing on the head proofs that don't converge rather than thinking about how can we make these proofs faster and just trying to prove as much as you can. Like how much of the chip can you actually do formal on?
That's
Interesting.
with your
actually a
limited
good
resources.
question. Like, where does the proof stop? Like, you mentioned verifying the RTL, but do we verify any of the translation after the RTL? We had this whole stack. Like, which parts are verified, which parts are unverified? Can we verify the whole chip or only parts of it? These are questions that I don't have a great sense for.
And I mean, that's when you get into like protocol. As soon as you start to get above a single like module or like unit within your hardware, you get into protocols and things like that and verifying that your communication protocols between these different components is working. But at the end of the day, you take your emulator. So one thing we do a lot of is emulation, where you take your chip and you put it on some very expensive hardware that's, I think, FPGA based. Don't actually know. And you basically fake your chip. So you fake your chip in software and then actually run stuff through that chip. So for our graphics teams, that will be like running video games on it. So you'll see the frames coming out of this fake chip, for example. And so that is a level of testing that we can do even today. And pretty cool, that you can actually fake a whole computer chip.
But
Maybe you
this
can't fake
is
a whole
but
thing.
this is like giving up and doing testing as fast as you can instead of verifying the whole chip because it's just too big, right?
I mean, it's way too big, right?
Yeah.
Like you always have this is, the whole abstraction thing of prove this component works like this, then you kind of jump up a layer. Now we prove this block works like this, and you keep abstracting stuff away, right? But
In the end of
that's
the day, you have proven some of the smaller bits formally, and you get like a real SMT proof. I'm gonna call that a real proof. And then at some higher level, you have these blocks that you prove correct, and then you have a protocol proof. That's what you mentioned. What's that proof in? Is it also in the SMT style, or is it like a hand proof? And then
protocols is where my domain, I'm afraid. So I can't really
interesting,
comment
yeah.
on like, communication around the chip. Um, the theory is all
So
based on, open source standards and things like that.
I
But
see. It's
I mean, this is
interesting
where
how varied
PCIe and
the
stuff like that,
like
right?
yeah, how varied the amount of verification and the standards that we have to meet at different levels of abstraction.
It's
yeah,
cool to see
protocol
like,
proofs, which I know a little bit about, oftentimes end up focusing on sort of okay, they need to care about sort of data transfer properties, right? You need to care about sort of what are called safety properties, which means you're not incorrectly sending the data or you're not reading the sort of the wrong piece of data. And you need to also care about liveness properties, which is that if I send the data, you will receive it eventually, right? Um, the state of the art, as far as I know, in this is all very manual still. There's some open source stuff that people have used to try to do sort of automatic term proving or automatic proofs that say that if I connect these two modules, there'll be no deadlocks. But I've also heard from teams at major chip companies, of which now there are software ones and hardware ones, that they have taped out chips and they found deadlocks in their chips after they have sort of fabricated their chip, which is I don't yeah, it's that tells you something about how bad it can get, right? Like the proofs we can do are very small still. And just making them scale up remains one of the biggest challenges.
I mean, one saving grace of protocol level stuff is that like PCIe is used by everyone, right? So we kind of think it probably works because there's so many, it's like a community sourcing of does this work? And like these bus protocols, how do we communicate data? Everyone uses fairly similar ones, I think. Maybe that's rubbish.
Is PCIe like within the processor, or is this processor communicating to other components? Because I
No
was,
idea.
but you can't verify the whole processor, right? You said that was too big.
Yeah. Well, it depends what you mean by verify the processor.
Like get the
I
SMT
understand.
style proof out.
But what does that mean?
Like
Like,
one big
does
query
this
to
process
your big verification machine, and it has like a full proof of the whole thing with respect to your processor's spec. That's like a dream, right? It's impossible for now.
that's what the formal verification dream would be indeed. But
I see.
I don't think that's practical.
That's not practical. And then my other question was, when you're lowering it, at what point do we have proofs for from the RTL down to the like gates that you're actually going to tape out? Like, is that
You
part
have
just unverified or?
you have proof from word level writing on a computer down to what I call the net list, so down to gate level. But then I have no idea if you have proofs for connecting up the wires correctly, uh, connecting up, like, I don't know, moving stuff around if you've got hotspots and things like that.
So
I have no
through
idea about that technically.
so from the Verilog down to the netlist, we do have proofs of that translation. I see.
That's
That's pretty
pretty
cool.
that's pretty solid.
Yeah.
But that's where the tool, because as soon as you have a tool, right, all these things are easy when you have a tool that's doing it automatically.
Right.
Because the tool knows what it's going to do and can tell any formal tool, hey, I did this, this, and this. The human trying to like do a bunch of optimizations and be like, hey, I did this, this, and this. We haven't really got that interface at all yet. And
I
like
see.
we can communicate it. So one thing that we tend to do a lot of in hardware design is if the proof isn't working, it's not converging, then we will break it up into a set of sub problems ourselves by hand, which is basically us saying, well, I did this, this, and this.
It's like leaving the breadcrumbs for the verifier. And it's the same thing that the lowering tool does, like your Verilog to netlist pipeline. Probably that automatic tool is very complicated, but leaves the like proof breadcrumbs for the verifier.
And as
I
soon as
see.
you can do that, you just make it, you give it intermediate points and it can have a good go at it, right? Like it makes sense. If I give you a whole, this is why children's exam questions are broken up into part A, part B, part C, right? You kind of slowly walk to
Right.
something more complicated.
Yeah. Yeah, there's this
I always thought
famous
it was just a way to get you to solve more questions than they say that you'll have to solve, you know. Like you have two
oh,
questions
it's
and
to
each
trick
question has
us.
10 parts. Yeah.
Yeah.
I
Yeah,
guess it's
well, we
actually,
need to trick the verifier into solving more problems than it thought it could, you know?
yeah.
I don't know. I mean, how much do you guys feel the influence of like these sort of tool generates proof in your world? Like I have a tool that's doing optimization. How does this then feed into my proofs, for
Well,
example? Like is that interface well established?
according to my advisor, generating a proof from your compiler, for example, and writing a verified compiler are like in spirit the same thing, which I still don't really understand. But like this idea of leaving the breadcrumbs and proving them all and connecting them all together with one proof and just like sitting down and proving the actual translation process itself correct. Apparently they're the same in some fundamental way, and there's a paper on this. But like if you write code to omit the proof, you're sort of encoding the proof that it's correct. The I guess the real difference is that only when you run the code do you get the proof for a specific input instead of getting a proof that it'll work for all inputs. So to me, the idea of like generating a proof for a particular input is sort of easier from a human standpoint than doing the like serious verification thing of your whole tool by writing it in some fancy language that's dependently typed.
Yeah, there's sort of the tradition of proof carrying code where you sort of try to do this encoding in the code itself, and it's supposed to sort of tell you why this program is correct. And then there's the other style of compilers, which are sort of more popular, but are fundamentally somewhat inspired by this other technique that do verification of the compiler itself, where they prove that for all input programs, if I take the program and compile it in this way, the program I get as an output is correct. And they define correctness and equality in the way we've been discussing as a semantic equality. Um, I would say the dream of like black box tool communication is a little less real in the way that like we don't often see tools where people build some system and they're like, here's like five proof related things I'm going to emit along with the statement I want to be proven. I'm going to send it to one of these lower level SMT solving tools and have them discharge it automatically. That kind of stuff is rarer in my sort of experience.
I mean, do you think it's farcical, if you think about it briefly, that you we take one of these big black box tools from a vendor and it generates some hints, and we pass that to some other black box tool, and that says, yeah, it's okay. And we just trust it.
Well, this goes
That
back
sounds
to sort
pretty
of the
farcical.
social. Yeah, this goes back to the social dynamics of your industry or something, right? Like the way you were describing this, the environment of fear almost, where people really want to verify after every run because the cost of mistakes is high. And people have somehow collectively decided that these two tools are good tools to use. Then yeah, I mean that's sort of what people believe. If you want to sort of come down to the real technical question of whether or not it's correct, is it's probably got bugs and probably the integration could be buggy and it sort of like could have problems. So one thing I was going to ask you, after you had pointed out that there's this like extreme environment of fear and you need to be able to verify everything before you need to push this into production. Um, what if you're not at a company? What if you're doing this as an academic or a hobbyist? And hobbyists can actually now produce their own chips. There's been a massive revolution in the open source hardware design world where people can go from high level hardware description languages all the way down to like fabricated chips completely in the open source. Um, what can we do differently? Where are sort of places that you think there would be room for innovation, or where the sort of industry is not ready to accept these kinds of technologies yet, but you see a lot of promise, I guess would be a interesting question.
Yeah. I mean, I think like universities and the hobbyists are just less adventurous and less dangerous in what they try and build to some extent. So that, probably most universities don't do super low level hardware optimization such that they can do like crazy stuff, right? Because if they start doing really clever optimizations, then they're more likely to introduce bugs. And then that's going to be really problematic for them, because they don't have the testing environment, the testing frameworks. So partly that's where these higher level tools that translate things down into lower level hardware, they provide libraries that do, a certain bunch of functionality, and you just kind of connect up these blocks. And then it's a much easier problem than necessarily building everything custom. Whereas in reality, when you do that, you're missing out on a lot of the optimizations. So certainly from a corporate perspective, from an Intel perspective, you can't meet the clock frequencies that we meet really by doing that sort of thing, And also, if everyone, if Nvidia, us, and AMD all use these same tools to build our chips, then to me it seems like you converge on the same chip, right? Like if you're
Mm.
connecting, like you can connect these blocks up in a different way,
Right,
but
right.
if you're using the same building blocks, then where these building blocks are quite large, right? Obviously, we use the same building blocks in that we use the same manufacturer, for example, but how you connect up these building blocks does have impact. But this is where we really kind of can differentiate between the companies. But I think for sure there's room, right? Why should the tools that do your high level translation down into these lower level building blocks not just carry on, right? Go more crazy, go a bit further and actually do some of the automated, or try and automate some of the stuff that people in the big companies are doing by hand. I don't think there's any reason to not do that. It just requires these tools to become a bit more low level aware. So I think one of the professors from UIUC said basically high level synthesis needs to become more kind of RTL aware. So it needs to become more aware of what's happening downstream if we're really going to see it take off. And just bringing that kind of, I feel like there's a lot of pressure
Mm.
from above, from higher abstraction levels, to be like, come on, let's write computer chips in crazy high level languages.
Yeah.
Whereas the reality is the industry is pushing up from the bottom saying, no, 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 please like make it more optimized and more hardware aware,
I
which
think
is this kind of tension.
this is a theme I'm seeing in hardware and verification in general, which is we sort of want both ways. We want the lower level stuff to get hints from the higher level stuff because you may sort of lose information and structure as you go lower level. But we also want to push the lower level stuff up so that the higher level stuff is aware of what's going to happen before it happens, since the problem is so hard. Like you were saying, that they should be more lower level aware. This is actually something I think Ratchet works on because he puts like the lower level details of timing back up into the types at the very high level of writing the programs. And I just wanted to note we're like running close to the time we usually stop the stream, so maybe we should talk a little bit about this idea in Ratchet's work and then wrap up the stream. Does that sound good? Great. And then any trailing comments or questions we have from the audience would be great too. Yeah. So did you want to chat about that, Ratchet? I think we haven't talked much about your work, and this is the perfect episode to do so since it's about hardware, and Sam may be interested too.
Sure, I don't want to. I think we should maybe mostly talk about what Sam does. There was someone who was curious about chatting about the new paper Sam had accepted. But like just to summarize the comment you made, Sam, about high-level synthesis, which is this area where people are like, okay, these low-level hardware description languages, they're too low-level. I don't want to write them. Let's use a high-level language to program and generate circuits. What high-level language, you ask? C++, of course. It's the best, highest level language of all languages.
Highest.
And so there's this entire area called high level synthesis where people take C++, System C, C programs, OpenCL programs, and compile them into hardware description languages, which then is further taken down all the way down to either fabricated chips or to these FPGAs, which are circuit simulators. And I think the point you were saying, Sam, which I think is very true, is that high level, you cannot treat the problem of compiling C++ to Verilog as the problem of how do I generate valid Verilog. You need to generate not just valid Verilog, you need to generate good Verilog. You need to, I think people coming into this area often mistake the ability to generate good Verilog with the ability to generate good architectures. Those are two fundamentally different problems. And so this point about like, when you're building these tools that can compile to Verilog, you should really be thinking about the kind of architecture you're going to generate. You can't just be like, I will generate Verilog that is correct and encodes all of my computations correctly, right? Like as a programming languages person, a very common thing to think about is like, I'll get correctness first and then efficiency secondly. That doesn't work. You need to think about the architecture first, and you also need to think about correctness, and you also need to be able to compile a large space of designs, and only then people care about what you're working on. So that's sort of one take I have in this area, which is, yeah, like you need to care about the low level details. If you abstract all the details, your hands are free, right? Like we were talking about the specification optimization problem, but your hands are so free that you're flailing. You don't know what you're doing. So you need some hints.
Yeah, Sam said that being free from the spec is very good, but you know, too much of a good thing may kill you because you don't know what to generate. It's so hard to write down like a good version of that high level spec.
I would say, I'm not in particularly high level synthesis space, but one criticism I would say of academia in this world is that it's like, if you're not reporting numbers that are like, oh, we achieved 1,000x speed up, 1,000,000x speed up, wow, it's amazing. Whereas, in actual low level circuit design world, we talk about 20 or 30% speed up or something like that. But the reality is that a lot of those 20 or 30% speed ups really add up over the chip, right? And so this lower level stuff, although it's probably less exciting, right? It's less like hot. And this is what we
I
saw
don't know,
in
20% for low level things sounds pretty good to me if it makes all my programs 20% faster, regardless of what they are.
Yeah, exactly. And this is what I would say we saw. They had a great panel at DAC that is one of the big EDA conferences. And they had basically academics in this high level synthesis space and industrialists. And they were so on a different planet from each other. There was the academics
Wow.
being like, let's keep pushing up higher. And there was the kind of industrialists being like, no, we're
No,
happy where we are.
that's not what
And
we
now it's
need.
all about like
Yeah.
pushing down.
Wow.
So there was a real disconnect there that was not super healthy.
Wow, that's really interesting. Yeah. There's like this
It's sort
we
of
need a bridge between these two worlds.
anytime you see 1,000x speed up for anything, you must ask yourself, why are they lying to you, right? It's just like 1,000x speed ups are not real. If you build an end-to-end system, you realize that most of these claims are often completely wrong. And to your point, Sam, that like 20% improvements might seem small, but like anyone who builds real systems knows that you can have like a 10x speed up in the small part of a system, but the end-to-end evaluation is what matters, right? And if your end-to-end is like only 2%, then your optimization, guess what? It's only 2% better. And so I think, yeah, we don't have to get into the academic discussion of like what are good evaluations and what are we really trying to build and sell to people. But I think anytime you see 1,000x speed up, that's kind of you have to be very, very careful about that. And people should be much more cautious accepting the claims that things are 1,000x faster than they used to be, because that would be really dramatic, right?
Maybe
Um,
I'll make one quick plug, given I haven't plugged my own work much today this time,
Please.
given the question about the data path. So someone asked about the paper that just came out in archive about data path verification, which I'm going to be at FMCAD. If anyone in the audience is at FMCAD, come and say hi. But basically, one of the problems we have, I've talked about in the formal verification world, splitting my problem up into these smaller sub problems and doing that by hand. And basically, what this paper is all about is saying how can we automatically kind of generate these smaller sub problems, kind of generate the hints from what human optimization has done, and kind of generate hints for our verification tool, which we can then pass off, and then hopefully, and you can turn a problem that wasn't solved by the tool into one that was solved by the tool, and one that was actually makes it speed up because you give it the breadcrumbs. Like it doesn't spend a whole ton of time wiggling around in no man's land. It just follows the breadcrumbs and gets their way faster. This is using this whole egraph stuff, which maybe we don't have time to go into
Never
today,
heard
but
of it.
Oliver loves it. Oliver's great. Look up any of his papers or presentations about it.
I mean,
But they're
Sam's the
great.
one actually using this in the real world for like the good of humanity and faster processors, which of course is what we all want. Um, but yeah, I'm very
so the,
excited about this.
yeah, there's this like Sam, correct me if I'm wrong, but I think this paper is in the line of work that uses really a very clean and sort of clever insight, which is that Sam described at the very start of the computation conversation. Sam described this pyramid of like uh, design principles that happen in sort of like real world circuit design, where you start with an algorithm and you slowly refine it, right? And you had this really sort of visceral image of this in one of your presentations where you were talking about how the algorithm can have the most impact on the final circuit that you get, but is the thing that we're least allowed to change, right? Once you decide on an algorithm, the rest of the people below the chain where they're building the circuit and they're running these tools and they're optimizing it for power, they have very little say and they have much less impact than something like changing the algorithm. Oh, I'm shouting, sorry. But one of the insights in your work in a previous paper, if I'm correct, on this is that you can use this thing called an egraph, which very, very briefly is something that lets you rewrite programs into equivalent programs and store all of their rewritten programs in a very compact data structure. You can use this insight to do a lot more exploration much more efficiently, and sort of do the changes at the high level where the algorithm is being dramatically changed, and also do the optimization at the low level, which is the only location you can actually do optimization and get feedback. And so I assume this work is sort of an extension to that, where you're showing all of these optimizations are also correct now because you can do verification.
I mean, all this work this paper basically does is it says any optimizer is actually also a really good verifier. Like you can take most optimization tools and you plug them into this egraph framework, and they're also a verification tool. You just kind of set the problem up differently, maybe add some stuff to it, but the underlying technology is reusable, right? Which is
Yeah, I
quite cool.
think lots of the things we think about as different are doing similar things if you treat them in a rigorous manner. Like optimizers and verifiers, if they both have to be correct, well, they're really doing similar things.
Also, like if you imbue your your you know verifier with the capabilities of your optimizer, then it should be able to repeat anything. And like,
Exactly, yeah.
sure, if that optimizer is a human, then we should imbue it with the powers of what the human is thinking about and what the human is doing. And reality is humans are a lot of times just doing rewriting. Like they're making changes to their program. Most people, 9 times out of 10 in circuit design at least, are not overhauling their entire architecture. They're making local changes, they're moving stuff around. It's not these grand scale optimizations. It's quite local, quite small, but a lot of small local changes, and they can, add up to something quite big. That's the notion I was trying to
Yeah.
capture.
I like it. It's a good overall picture, like bridging the gap between what people are doing, what compilers are doing, high level, low level. We've gone over a lot of these sorts of problems in hardware, which is where they're perhaps most poignant because you have to go so far down to get to the hardware.
It's really nice to
Yeah.
be part of this sort of e-graph entering into hardware design space. It's a really great example of where programming languages technique is kind of moving across the dividing line into a different realm. And it's really exciting to see people kind of pick up on that. Some people at Cornell are kind of picking up on that and getting excited about it. So
Some people you said.
Great.
some people,
Yeah.
Yeah.
I'm not actually referring to you, Rajit, to be honest, but
I know the other person too. He's a friend. Um,
Great.
oh, that other person is my advisor. Never mind. But yeah, it's egraphs are actually a interesting example because they flitted back and forth between the hardware and the PL communities, right? The origin, well, PL and our hardware had like a deep connection, or PL or and formal methods has always had a deep connection to hardware design. The development all these formal tools like SMT solvers and SAT solvers comes from the fundamental problem of verifying hardware, right? That was the thing people are trying to do, and so that resulted in the design of SMT solvers, which internally have egraphs, right? Egraphs are a really old data structure that people have used forever to do these kinds of equality proofs. And then, so they were a part of the hardware world. And then there's this work from Oliver's lab where they showed that you can do it much more efficiently. And because program rewrites, as you said, Sam, where like a lot of the time, the fundamental thing we're doing is we're taking something that already exists and rewriting it to an equivalent form to optimize it or to change its behavior on sort of the amount of power it consumes and stuff like that. That's such a powerful abstraction that like egraphs are now sort of one of the big ways that you can use to rewrite your programs and optimize them and sort of change them. And so they're back in the PL world. And then again, hardware people are adopting them again. So it's just like everything that comes around goes around. And
Yeah, it's kind
so
of
it's
funny.
it's quite
We just yoinked it right out of the SMT solver and like made everyone use it themselves, and it's actually works pretty well, turns out.
I mean,
yeah.
the
Exactly.
question I would ask is does all it take just someone to produce a good, extensible implementation for anything, right? For it to turn out to be really useful. Like, I'm sure there's lots of things that's not true for, but what's missing, right? Like, Max just produced Oliver's colleagues just produced this really great library. Oliver involved, loads of other people involved, but really easy to use, extensible. And what other gold is out there for us to just like really take something like an egraph or any other data structure and just have that and pluck that out into loads of different applications?
Yeah, sometimes the barriers are just straight up engineering, like very human reasons. You need to have one good library that everyone understands and can be used out of the box. And, once you solve that problem, sometimes like the innovation built on top of that is very valuable.
Yeah. I feel like to answer your question, Sam, it was like, what else have uh, could be sort of amenable to such kind of use? One area that I really feel a connection to, but don't see it that often, is like randomized data structures and randomized algorithms in general have not been a very mainstream focus. And like again, I don't know that much about them. The ones I know about, I'm always like, oh my God, this is amazing. Like skip lists, when I learned about skip lists, I was like, incredible stuff,
Well,
right?
I'll have to learn about
And
those.
so yeah, and it's sort of a thing that has not really pervaded it's like a data structure that has not pervaded programming in a way that I don't know, something like hash maps do. Um, and so that's one area. I don't know. People who know about randomized algorithms, go make an amazing library, and we'll try to use it for
Or
things.
if you know about them,
Uh,
maybe we'll have you on the fork join and we'll learn all about them.
right. Yeah, if you know about randomized
But
algorithms, hit us up. We'll have you at ForkJoin, and sort of chat about it. But I think the maybe I'm just like pandering to the crowd, but like formal reasoning for statistical non-deterministic things is one area where there's obviously a lot of hype, but there's a lot less sort of like hardcore formal tools to use in the same way that we have done for discrete logic, which is the foundation of what you've talked about today, Sam. So we're almost out of time. We have this uh, one episode old ritual where we ask our guests to just mention something they found interesting to read in the last couple of weeks or interesting watch, technical, non-technical. But just to close out, we would like to hear from you. It's like three things that you found that were interesting to read or watch. And then for anyone coming from the software side who's interested in hardware, if you have any advice or pointers. And I'm putting you on the spot, so I apologize for that. But
We should
still, if you
uh
have,
we should call this the ice refreezer because it comes at the end.
that's right.
Like a
It's not
classic
a nice.
like icebreaker question, but we do it at the end.
so let me
We
try
do
and
it
do.
at the
I'll
end.
try and do one technical, at least
Yeah.
on my field. So particularly recently, I've started getting to look at how do we construct pipelines and timing within our circuits so that it's like, how many cycles is it going to take? We talked about clock cycles and how many cycles is it going to take and things like that. And one recent work that I kind of relived a little bit, someone from Berkeley called Alan Mashenko he's one of the founding fathers of this tool called ABC, which is sort of a low-level logic synthesis tool that does the gate level construction, right? He did this really interesting work about, well, we need to be aware of timing. So it's a bit like Ratchet's work as well about having this awareness of timing while we're also doing these low-level optimizations. So it's bringing, this multi-objective optimization back together where traditionally they're more separated. So it's exactly like Oliver was talking about kind of bringing information up the stack. So I was really interested in that work. I think that came out last week, something like that. No, last year, this year, something like that, about retiming and being aware downstream. Gosh, other things that are really exciting at the moment. I'm kind of interested in rewrite rule synthesis at the moment as well. So I think there's some work coming out from Oliver's lab. I'm going to plug them, but that's coming out at Uppsala, maybe.
Yep.
But all about, how do we take rewrite rules and understand when they apply, what kind of situations they can apply in. So this is really relevant for any compiler people who have rewrites in your system. So LLVM stuff has a bunch of rewrites in it, and there's all these different conditions about when you can apply them. And I think that's kind of an interesting space. I had some really great chats with John Regier at PLDI. He's a guy from Utah. All about this domain of synthesizing rewrites and synthesizing conditional rewrites and all that sort of stuff. So that was really interesting.
Yeah,
And
the
then,
compilers people also call them peephole optimizations, like
yeah,
small bits of syntactic things that you can apply to programs.
and then third, I don't know, I've been really into those like CNBC videos recently about like the train system in America and why the train system is like it is. So check those
CNBC.
videos out. But definitely maybe not CNBC, but one of the arbitrary C beginning news outlets in America that has a yellow background. But they're really interesting. Long format news is my new big thing. Guardian Today and Focus podcasts as well are excellent. So this is mine. And the other
There's
topic,
this.
Sorry, go on.
Sorry, just to comment one thing. There's this weird overlap between all my friends and people who love urban planning. Like the number of people who talk to me about urban planning and trains, it's great. I love it. I'm a huge nerd about these as well. I was listening about to this podcast. I think it's called Disconnected. And it was like a 7-part series on the Texas blackout
Oh wow.
that happened 2020 is like maybe through NPR. But again, it teaches you a lot about the grid, and I'm just like, yeah, it's so funny that so many people I know are just like into the grid or
The
like into
grid.
like urban planning
It's the
things.
grid,
Yeah.
man.
For a European who comes to America every now and then, you know, the shocking difference between the way our cities operate and the way your cities operate is always an interesting topic. And you think you're gonna hop on. I get off a plane and I forget that I'm America and I can't just hop on public transport of any domain.
Sorry. Yeah.
Yeah,
Just saying there was one last thing.
yeah,
Maybe
Oliver.
I
Oliver,
interrupt.
you wanted three things and then something else.
I
Can you
did.
remind me?
I
I
can't
can't
remember.
remember.
No.
No, we
The
don't.
last one I said, that was on Oliver, that was me. The last thing I said was for people who do software but are
Advice.
interested in yeah, jumping into hardware. Advise people to follow, I don't know.
For sure, I would go look at my supervisor's. He does a blog post where he talks about hardware design a little bit and like kind of mathsy style hardware design. So look up George Constantinides from Imperial. He does a great job there. Our group has a website with various pointers on it, so that you can look up the Intel Numerical Hardware Group. That's a kind of not particularly easy access place, but for sure. I gotta say, I'm probably not the best source of tips on how to get into hardware design as an inviting level, but certainly there are some great open source tools now. So things like Yosis is a great way you can actually realize, kind of take some circuit design and actually go and play with it. Or recently, I know that some of the Washington crowd are really obsessed by these games. So maybe Oliver can describe them or give me the name of them, but about how do you build a CPU. I
Yeah,
think
there's
Max
these
is like
super
super into
good
it.
games now for building CPUs and they can teach you hardware. What's it called though? I can't remember.
Turing, I think it's called.
Say it again.
I think it's Turing Complete.
Turing
Mm,
Complete. Yes, that's what
right,
it's called.
right.
Yes, play more
Yeah,
video games, everybody. That's how you get into
Okay.
that's
hardware.
right. I think there's one thing away
Maybe
from.
that's the fun way.
Yeah. All
Yeah, and if
right.
you're listening to us on Spotify, all of the links will be in the description for the episode. But yeah, let's wrap up.
Great. Thanks for being on the Fork Join, Sam. It was a pleasure. I think this was a really great episode, and thanks for asking questions in the chat, everyone.
Thank you very
Yeah,
much for having me, guys. It's really fun. Like it's really fun to talk about these subjects and particularly with people who are maybe on a different side of the spectrum from
fence.
academic. So
Yeah. We'll be back 2 weeks from now on August 19th. And I think we have a tentative guest already. I
I
think it's
think,
Remy.
yeah, I think Remy, who is a database person, will hit another area that's PL adjacent. All
Yeah,
areas are not their own areas, they're just PL adjacent, it turns out.
that's right.
So,
That's right. The kind of PL areas we like.
yeah, so it should be really interesting. Database systems are very powerful, and we'll hear all about them.
Yeah, and Remy has done again foundational work on things like the join algorithm, which if you know about databases, that's what underlies everything. And is again one of those problems that you don't think anyone needs to solve anymore, but Remy has a great depth of knowledge on how everything works. And so yeah, please come by. We'll see you 2 weeks from now. And yeah, thanks, Sam. See you around.
Bye.